everybody. So yesterday we were discussing hierarchical clustering. So we said there are two kinds of this kind of clustering: agglomerative and divisive. So in agglomerative, we start with the points, the individual points, and progressively combine them, merge them to form larger and larger clusters. And finally, you end up with only a single cluster, which is the entire data set. In the divisive clustering, you do the reverse process. You start with one big cluster, which is the entire data set, and keep on splitting it progressively until you get to a point where every point becomes a single cluster. So this is one example of divisive clustering is our bisecting k-means clustering, which we discussed in the last class. So today let us look at agglomerative hierarchical clustering. So basically in this you have to compute the proximity matrix, right? And initially every data point is a cluster. So then at any given stage you see which are the closest 2 points or closest 2 clusters and merge them into one cluster, right? And repeat the process until all the points merge into one cluster. So let me elaborate on this because there's some important issues here. So first you compute the proximity matrix, which looks like this. Suppose I have some 5 points, and then I look at the distance of every point to every point and compute the matrix. Now, so thing is, like I said, if you just have single points, right, and initially you'll have single points, then you can see which is the smallest entry in this, smallest distance. If the proximity is taken as distance, smallest distance, and then you merge those 2 points. So then the proximity matrix reduces by 1. That is number of rows and number of columns goes down by 1 when you reduce 2 points, and those 2 points now form a cluster. Now, so as you keep doing it, at some point you will have a bunch of clusters, okay, because points now form clusters. Now, how do you apply the concept of proximity to clusters? Because you can apply the concept of distance or proximity to points, but how do you apply it to clusters? So this is the crucial question in hierarchical clustering. So what happens is, so there are 2 ways to do this, and there are several ways to do this. So, but basically, when let's say you have 5 clusters, when you find that 2 of the clusters are close to each other by certain measure, whatever be the measure, then you reduce the number of rows and number of columns in the proximity matrix by 1. So in this example, you see that there are 5 clusters. So C1, C2, C3 up to 5, and so you have 5 rows and 5 columns in the proximity matrix. So then you combine C2 and C5 to form a new cluster, which is called, let us say, C2 union C5. That's the name of the cluster. So then instead of C2 and C5, you have a new column named C2 union C5 and a new row named C2 union C5, and the previous rows for C2 and C5 are gone. So now you have proximity matrix of size 4 by 4. So that's how it works. But the problem is, how do you compute the distance between 2 clusters? So here there are many ways of giving this a distance measure between 2 clusters. So intuitively, how do you formalize the notion of closeness between or distance between 2 clusters? So here are several options: min, max, group average, distance between the centroids, and so on. And then there's this method called Ward's method, which is based on an objective function. So let us look at them one by one. The first one are the min kind of a measure of distance between 2 clusters is like this. So if you have 2 clusters shown in this slide, right, you have both have 4 points each. So min means look at all distances between all possible data points. Okay, all possible pairs of data points between the two clusters, right? And take the smallest among them. So this is the closest. These 2 are closest between these 2 clusters. So this distance is taken as the distance between the 2 clusters, the entire clusters. You take it as surrogate for the distance between 2 clusters. Then you have max. Max is kind of the opposite. Take the 2 pair of points, one from this and one from this, such that the distance between them is the highest, is the maximum, right, among all such pairs. And that distance you take as the distance between the 2 clusters. Then group average is more exhaustive. it's because min and max represent extremes, because they're not very representative of the real distance between two clusters. Right? But sometimes um, the clusters can also be slightly overlapping. It's possible, right? So they represent extremes. But group average, in group average, you take every possible pair, distance between every possible pair of points, one from here, one from here, and take average of all those distances. Right? That's a more representative, but obviously it's computationally more intensive. Then something in the spirit of k-means, which is computationally not that intensive, but it has its own problem, which is distance between centroids. It takes centroid of the first cluster, centroid of the second cluster, take distance between them. And that you take as a representation between the two clusters, of distance between two clusters. Then there is something called Ward's method. I'll come back to that later. Now, if you look at the cluster similarity, right, or proximity measure of min, which is also called right, single link similarity. It is based on, like I said, it's based on the closest points in the two clusters, right? So that means it is based on only one link in the proximity graph. So, for example, if you look at this, right, this set of points, this is very small data set. There are just 6 points. Then, so you can, the points are shown graphically in this figure. This from the textbook, right? They were prescribed textbook, and the data points are given in this table. So Euclidean distance, the proximity matrix or distance matrix, is computed in this table 8.4. So now, which is the closest among all of them? Okay, so 3 and 6 happen to be the closest. So you can see that the 3, 6 distance is 0.11. That is the smallest distance, right, among all the distances. So these two you combine first into one cluster, right? Next distance, so this is a 0.11. Next distance like that is 5, 2. So if you see 5 here and 2 here, it is 0.14. So that is the next highest value in this entire table. Okay, so you have 3, 6 first and 5, 2 next. So you see that when you compute the dendrogram, you take 3 and 6, right? You take them up, and they are combined at some point. And what is this point? This point is the proximity measure or the distance measure. So as you keep on combining, the clusters get bigger and bigger. So distance measures also get bigger and bigger. So therefore, they combine at higher and higher levels. So that's how you form this kind of a tree structure, which is called a dendrogram. Dendro comes from tree. I guess it means tree. So the merger of 5, 3, and 6 happens. No, when you merge 3 and 3, you know that the proximity between the two is 0.11. So in the y-axis is the proximity. Right, and so then 2 and 5, the proximity is 0.14, right? 0.14. So these two are merged. So this level is 0.14, this level is 0.11, and they are merged. And then the next, right, happens to be this, because we are using the min measure of proximity between clusters. So by min measure, the proximity between these two clusters. So now there are only 4 players. That is the cluster number 1, cluster number 2, data point number 1, and data point number 4. There are only 4 players. In the proximity matrix, we'll have only 4 entries or 4 entities. We have 4 rows and 4 columns. So now, if you look at all possible distances, the proximities, if you take, let's say, cluster 1, right, distance between cluster 1, cluster 2, cluster 1 data point 1, cluster 1 data point 4. Okay, like that you take all distances. The distance between the cluster 1 and cluster 2, since it's based on min, it is equal to the distance between 0.2 and 0.3. And 0.2 and 0.3 distance is actually only 0.15, which is just higher than the previous distance between 5 and 2. Okay, then that is the third largest, from the bottom, right? So therefore that comes next in the ordering. So first this, then okay, had you taken max, you won't be merging these two clusters in the next step, because max would be distance between 5 and 6. Therefore, that will be a much larger value than the distance between, let us say, this cluster and data point 1, and so on. So therefore, it all, the sequence in which you merge clusters depends upon this measure, right? Measure of distance between clusters. So 2 and 3 will be closest, will be taken to be the closest. Therefore, you merge these two clusters. So now you end up with, so that merger is shown here. 3 6 is merged first, 2 5 merged first. These two guys are together merged at next level, which is 0.15. Then you get a huge cluster, and now you have three players in the picture. Cluster which is numbered 3, data point 1, and data point 4. So now if you look at cluster 3, which is the distance between this and 1 and this and 4. So you need to see which is the closest point. Probably 2, I don't know, 2 or 3 will be the closest point to 1. And 3 seems to be closest to 4, right? And by that measure, between the entire cluster, 4 seems to be closer, because 4 seems to be closer to the cluster 3, right, than 1, than data point 1. So therefore, in the next step, you merge this entire cluster 3 with data point 4, which is what is happening in the figure. So and that is equal to the distance between 3 and 4. So how much is that? That's also 0.15. Okay, so it's they're showing it about the same level. So this merger distance is happening at about the same level. So that is 0.15. So 4 is merged here. Next, after this, you have included 4 also in this cluster. So this big cluster has 5 points, right? 2, 5, 3, 6, and 4. All these points are merged into one cluster, which is numbered 4. That cluster 4 is now, there's only one point left, so you have to only merge with that. So that is shown here. And when that is done, so among all these 5 points, which is the closest point? So if you are merging a single point with a cluster, so if you have a bunch of points in a cluster and there's another single point outside, how do you decide the distance between the cluster and the single point? Again, the same rule, it's mean rule, right? So this end point and this single points seem to be the closest. So that distance is the distance for between the cluster and the point. So in this case, probably it is 1 and 3, and that is some, 0.2 something. So let us see what that could be. So 1 and 3 is, yeah, 0.22. So that is the thing. So 1 and 2 is 0.24. That is higher. So 1 and 3 is closer. So 1 and 3 is closer than 1 and 2. So therefore, right. So next you merge with 1 at this point is 0.22. Right after that, it's a single cluster. So that is how you perform this kind of a agglomerative or hierarchical clustering. Now the strength of this min type of min proximity measure to perform a hierarchical clustering is that it can handle clusters of different sizes. See, for example, you have two clusters, one is small, one is big, right? And if you perform this kind of a hierarchical clustering, you can get these two clusters separately. Now, what do we mean by saying that you can get these two clusters? So basically, what this means is when you grow the cluster, you start from single points, and keep on taking them up and you merge them, right? So as you keep merging them, so the small number of data points will merge, and then the large number of data points in the second cluster will also merge. Okay, and at some point you'll have two clusters, and they also merge. So basically, if you construct this dendrogram and cut it at some point where there are only two branches or two clusters, that will be something like this. That's what they're saying. That's what is meant by saying that it can capture, it can get these two clusters. And it can also handle non-elliptical shapes because the prototype-based clustering is biased towards globular or more spherical shapes, right? Whereas with min and hierarchical clustering, you can, in principle, even capture non-elliptical clusters. But problem is it is a bit noise sensitive because it is when you're merging two clusters, the distance between two clusters is taken as not some kind of distance between the core of the two clusters, but only it is based on the nearest points. So it can be a bit sensitive to noise because the noise point can be can make two clusters look closer than what they actually are, right? So therefore, so when you have two clusters like this, instead of picking this as one cluster and this as another cluster, it can get messed up. And so look at this. The blue points are one cluster, red points are another cluster. So they are quite interspersed. Blue points are quite interspersed with the red points. So it is not able to pick up the two clusters in a clean fashion because of the noise. So the next method is called max or complete linkage. And so here the distance between two clusters is taken to be the distance between the farthest pair of points in the two clusters. So determined by all the right. So again, let's take the same simple data set of 6 points, right? And the proximity matrix or the distance matrix is given. Now, so now again, the first step is just like before, because the cluster to cluster distance doesn't arise in the first step because you have only single points. So this is okay because when you have single point, distance is simply the distance, the Euclidean distance. This max measure comes only when you have clusters in picture, right? So similarly, at the next level also, the measure is simply the distance. So again, up to this point, it is same. Now you see there is a deviation. In the previous case, where we used min measure, in the next step, we merge this cluster with this cluster. So this is what I was saying earlier also, right? But in the current case, where we're using the max measure, the distance between the cluster 1 and cluster 2 is not distance between 2 and 3, but it's a distance between 5 and 6, which is very high. So it is it kind of overestimates the distance between clusters, this max measure. So you don't try to merge these two clusters. The next thing is, so now, so distance between this cluster number 1, which has 2 points, and data point number 4 is now max. That means between 4.3 and 4.6, you see that 4.6 is longer. So therefore, that distance is taken as the distance between this cluster and this point. But even then, even though even if you take like that, right, this distance seems to be smaller than, for example, the distance between this cluster and this cluster, or the distance between this cluster and this point. Okay, so that's how it is. For example, 4 and 6 is 0.22, whereas 4 and 3 and 1, 3 and 1 is also okay, 0.22. So there's a tie, right? So for some reason they have taken this distance. Okay, so they merged with this data point. So now you have 3 players: cluster number 3, cluster number 2, and data point 1. Okay, so you see that 3 and 6 are merged, and then it's merged with 4. And so 2 and 5 are also merged independently. In the next step, it turns out that this is closer, right? So the distance between cluster 2 and data point 1 will be a distance between 5 and 1 because of the max measure. Okay, and right, and finally, you have only two clusters, two players. You just merge them. Right, that gives you the complete cluster. Now you might have noticed one more thing in the dendrogram. So there are 6 points. You see that the points are not placed in their natural order, 1, 2, 3, 4. It's not like that. So their points are placed so that nearby, so points which are clustered, right, in this clustering process, are placed close to each other in the x-axis of this dendrogram. Therefore, 3 and 6 are placed to. Otherwise, what will happen? You'll have a lot of intersections, right? A tree should not have intersection. That's a you depict the tree properly. You should not have lines, cutting each other. It looks very ugly. So 3 and 6 are next to each other. 5 and 2 are next to each other. And 4 is brought closer to 3 and 6 because 4 will merge with 3 and 6. 1 is brought closer to 2, 5 because that will merge with 2, 5. So this kind of so whereas in the 3, 6, 4, 1, 2, 5, that's what you have here. In the previous case, that was not the order. So that 3, 6, 2, 5, 4, 1. So the order is different. This ordering is based on how the points are progressively merged in the clustering process. Okay, so that is necessary to construct the tree diagram. So that is how you do the hierarchical clustering with max measure. The strength of this is it is less susceptible to noise and outliers, unlike the min measure. This too has limitations. Sometimes when it, even when you have clean clusters, not much noise, sometimes there's a tendency to break up the large cluster into smaller clusters. And this is biased towards globular clusters. Then group average is the one which is more balanced because min and max take more extreme positions. In group average, you take the proximity of every pair of points such that Pi is in cluster I and Pj is in cluster J. And take sum of all the proximities, divide by number of clusters, number of points in cluster I, number of points in cluster J. So the size of the clusters. Right, so this is the average, quite computationally expensive. If you do that again, I won't go through the whole kind of narrative, right? A description, point-to-point description, more like a cricket commentary. So we'll just quickly do that. Again, at the up to first level, it is the same, right? 3, 6, 5, 2, and up to this point, it is the same. And then you have again combined with 4 with group average, right? So here you see that different from both min and max. In the min case, we combine cluster 1 and cluster 2. In the max case, we combine cluster 1 and cluster and data point 4. But we combine cluster 2 and data point 1 as a next step. But whereas in group average, right? So it all depends upon your choice of data. You cannot draw any very general lessons out of this, right? And after that, you combine the whole thing. Okay, so again, here also you can see that the ordering of the data points on the x-axis is quite unique to this measure. So the advantages or strengths are the less susceptible to noise and outliers. Limitations, this is also biased towards globular clusters. Then finally, you have something called Ward's method of similarity. So in this case, basically you look at the increase in the sum squared error when two clusters are merged. So smaller clusters obviously have smaller sum squared error. So when you take two clusters, okay, so call this C1 and C2. Oh, sorry, C1 and C2. And so C1 has an SSC, which is called SSC1. C2 has SSC2. So now if I combine this data set and calculate SSC, that will be called SSC. I'll call it SSC or SSC12. Okay, so the increase in the sum squared error when two clusters are merged, right? That is called that is SSC minus of SSC1 plus SSC2. right? So that increase is taken as the distance. So distance between C1 and C2 is given as this increase in SSC. Okay, so which is also computationally quite expensive. And the properties are it is susceptible to noise and outliers. But it's biased towards globular clusters, right? And it's a hierarchical analog of k-means because so the thing is what the other methods don't have until now is none of these other hierarchical clustering methods have any objective function, right? You should have a proximity measure because you should always have a proximity measure whenever you do any clustering. So that is the basic. But beyond that, there is no objective function in any of this min, max, and group average and all that. In the Watts method alone, for the first time, and among the hierarchical clustering methods, we have an objective measure, an objective function, which is the SSC. And the difference in this SSC is taken as the distance between the measures. So therefore, since in k-means also we take the same objective function, SSC, right? You can use this to initialize k-means. So the problem with k-means is it's so sensitive to initial conditions, right? Whereas in hierarchical clustering, generally it is not sensitive to initial condition because, right, there is a unique trajectory starting from the very first merger that you make. At every stage, once your proximity measure is given, right, the whole trajectory of going from right the whatever n cluster to one cluster situation, the trajectory is completely determined by the distance measure, and there is nothing like dependence on initial condition. So therefore, you can think of these clusters you get as more reliable, especially when you do it using Watts method, since the basis is also similar. It's based on this same objective function. You can, if you want k-means, then you take this tree and cut it at a point where you have k branches. Okay, so whatever you cut here, so let's assume that is equal to k. And at that point, you take the clusters, whatever you have, and use that to initialize the k-means. But all this is obviously, very expensive. So this picture gives a comparison of all the four methods. Like I said, the first step where you start at start with single data points, all four methods give the same answer because simply based on proximity. The cluster to cluster distance doesn't arise at the first step. Right now, if we go to second step, also it is pretty much the same. Then from third step onwards, things start diverging. Right. So all these three, Watts, group average, and max, took one route, and min alone took a different route. Okay, so that is about the four different kinds of hierarchical clustering techniques. Now, if you look at the complexity of this algorithm, so it is order n square. So in terms of memory, it takes order n square space because the proximity matrix is of size n square, has n square entries. In terms of time, it is kind of order n cube because there are n steps at each step, and the size is n square. The n square size proximity matrix has to be updated and searched. But the point is, the proximity matrix keeps going down at every step. So strictly speaking, you don't have to search the entire n square at every stage. So there are reduced complexity measures, right? Because normally, if you have dummy entries in the complexity matrix after every merger, then you have more computations. But if you keep on reducing the complexity matrix dynamically, then the complexity is reduced, and so there are some approaches where complexity can be reduced to order n square log n. So it is not n cube, but n square log n in terms of time complexity. So thing is, there's some problems with this. Once you merge two clusters, you cannot unmerge them or undo that step, and there's no object function is directly minimized. Even in case of the Watts method, you are using objective function with SSC to define a distance. The whole tree is not derived directly by minimizing some objective function, right? So similarly, different schemes have problems with one or more of the following. So each scheme has some strengths and some disadvantages. So the problems that most schemes face is in these areas: sensitive to noise and outliers, and difficulty in handling different size clusters, and right, general convex shapes, and breaking large clusters. So next, what we will do, I want to introduce a very different kind of hierarchical clustering called scale-based clustering, right? And to introduce that, I need to introduce a slightly different kind of clustering algorithm. It is based on the same objective function which the k-means clustering uses, but the clustering process is slightly different. Okay, this kind of a clustering method is called competitive learning. It's an online clustering algorithm. So in k-means, you have two steps, right? In k-means, you have uh, allocation step, and second step is centroid computation. So thing is, when you compute the centroid, you take all the points in a given cluster and take average. So you, in one shot, the centroids move in big jumps, right? Because when you allocate, the clusters change in a significant way. A lot of points come in, a lot of points go out. Therefore, centroid computation, when you perform the centroid computation, the update of the centroid from one iteration to the next iteration happens in big jumps. So whereas in online clustering algorithm, the centroids are moved in incremental steps, in very small steps. And this is done by performing gradient descent on this cost function. What is this? Sorry, this objective function. What is objective function? This is nothing but our same sum squared error, SSC. I'm just using it, writing it slightly different notation because that will make my gradient descent equation derivation easy. So basically, let us see what the expression is saying. M is a centroid, Mi is the ith centroid, Xj is the jth data point, J goes from 1 to n. What is this saying? Mi, this notation, Mi of J means centroid closest to Xj, because Mi is a function as if it's a function of J. So because what are we doing in SSC? If you take two centroids and bunch of points. So these three are closer to this one, number one. These three are closer to this one. So you take all these distances, right? Sum them, square them. Square them and sum them. That is for this cluster. Similarly, take all these distances, square them and sum them. That's for this cluster. Then add them up. This is your sum squared error. So what are we doing here? For every data point, see which is the nearest cluster center, the centroid, which is Mi of J. Then take the distance, square them, and sum them over all Xj. So this is a very more compact notation than what we had before. So now our objective is, given the data set Xj, what are the centroids Mi which minimizes cost function? This is what we have been trying to do in k-means. Right? K-means is meant to minimize this exact same cost function. Only thing that we are doing now is, we are doing this by incrementally changing MIs in small steps by using a process called gradient descent. So what is gradient descent? So we'll encounter this concept of gradient descent repeatedly in this course for many algorithms. Let me just give a small example. Suppose I want to minimize a certain function. So let's say f of x, and this is x. So normally you can just take the derivative and then f prime is equal to 0 and you get this point. Okay, but assume that we don't have that option because for whatever reason, f could be a very complicated function. F is n-dimensional and hugely nonlinear and so on and so forth. The picture can look very deceptive, but the actual form of f can be very complicated. So then you cannot just solve the derivative and make it 0 and solve it. It can be very complicated. So therefore, what you do is you start at some initial guess, right, for the minimum. And then from that point onwards, you need to go. So the actual minimum is here, right? I'll call this x, the solution xs. Okay, and initial point is here, x naught. So how do you go from this x naught to xs? So, so if you see whether you have to decrease x naught or increase x naught, that can be simply found out by the derivative. So since the slope of the tangent here is positive, the slope of tangent is positive, right? You end up going to the left, that is x naught is decreased. Whereas if your initial point is on this side, right, the slope of tangent is negative, so therefore you end up going to the right side. So if the slope of the tangent is positive, you decrease your x. If your slope of tangent is negative, you increase x. If the slope of tangent is 0, don't change. So this can be simply captured by this kind of an update rule, where delta x is proportional to the negative of df by dx. So if you do this iteratively, right, you'll finally go to a point where this is minimum. Or this can also be done as delta x is equal to some minus eta df by dx. So this is in case of, right, where x is a real number. Whereas if you take an n-dimensional case, x is in Rn, then instead of derivative you have gradient. So delta x is proportional to minus of del of f with respect to x, right? Or this can also be taken as right. So that's all. So this is called gradient descent. So we'll do exactly this, right, to derive this kind of an online clustering algorithm. So this is the cost function, right? How do you differentiate this with respect to mj? So actually let us imagine that there is a factor half here, because then if I differentiate this power 2 will come to the front and 2 and 2 get cancelled, right? So you get so basically you will have a gradient of E with respect to mi will be mi minus x. Okay, so you have 2 and 2 get cancelled, right? So now if you have negative of this, okay, so you have so delta mi is equal to minus eta del of E with respect to mi. So that we give minus eta mi minus x is equal to eta into x minus m. So what does that mean? So first of all, note that this is not just any x and any mi. The mi happens to be the one which is the closest centroid to given x. So that is implied here also. So mi is the closest centroid to x. So that is given. Okay. So that means if I have two centroids, I'll call this m1 and m2, and my data point here is x, right? So I look at take the nearest centroid, which is m1, and apply this rule. What does the rule say? Move mi in such a way that it is proportional to x minus mi. That means move it towards x a little bit. And how much is little bit? That is given by eta. So eta defines the step size. The jumps by which you move, usually it will be a small number, like 0.1 or 0.05, some very small number. Right. So you are moving your centroids towards data points. So next, maybe I take another data point which is somewhere here, and this data point, for this data point, the nearest centroid is m2. So I take m2 and move it towards this. So I keep on doing this for all data points, and ultimately I get a solution which will minimize this SSC. Now, just like in case of k-means, k-means also tries to minimize SSC, but it will go to a local minimum. Here also the exact same thing happens, because when you do gradient descent, the equations only assure you that you will go to the local minimum, right? The nearest minimum. They don't tell you. Suppose you have lots of minima, uh, you will only go to the nearest one if you just pursue gradient descent. Okay, so this is the online clustering algorithm. Now, how do you apply this to find out what is called scale-based testing? So first of all, to understand what is, and I'm saying this is a kind of a hierarchical clustering algorithm, where the clustering is based on the concept of scale, right? So what is a scale? Let us illustrate that using a one example. Now, can somebody tell me how many clusters are there in this data set? Anybody? How many clusters?
It might be two or four
Yeah,
or three, right?
yeah.
Depends
How
on
do you
like how
decide?
many points we owned in one cluster.
No. Is there any other way you can say the any other basis for the choice that you can think of?
Some threshold for distance, maximum distance between like the nearest points we call the cluster.
Hmm. Correct, correct. So you can take some kind of distance measure, right, as some kind of a scale, and you say, okay, how many clusters are there at this scale? So if I take my scale as maybe a distance of about that big, and if I say how many clusters are present, right, that will give rise to 4 clusters, because then I'll have this, 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 and this. They're all at the same scale. But if I takes my scale to be something like this, right, then I'll have just 2 clusters. So the question of how many clusters are present has no meaning unless you specify, give some additional information. So in this case, that information that we want to supply is the scale, and given the scale, you can give different number. So look at this distribution. This is histogram of a data set. This is a one-dimensional data set. X is in Rn is R. Right now, how many clusters are there in this data set? What will you answer? Anybody? The Kishan keeps asking questions. Yeah,
Again depends on scale, right?
yeah, very good.
It's
So
again depends on scale, right? We can see there are four clusters, there are 8 clusters, 10 clusters.
right, right, right. So if I take the scale as something like this, I'll have 4 clusters. If I take the scale as something like this, I'll have only 2 clusters. Okay. So the idea of scale, right, as determining clusters is a very important idea. A lot of applications of that idea. And if you combine this idea of scale with our previous algorithm, which is this competitive learning or online clustering algorithm, then you have very interesting algorithm for hierarchical clustering, which is called scale-based testing. So in the previous method, right, this method, we have a way of going towards. So your mi delta mi is given as eta x minus mi, where x is sorry mi is closest to x. Okay, so first among all mi's, right, mi is close. This particular mi is close to x. That's what we mean. Only then you can move it. So we are not moving every centroid to every point. That's not correct. Now, without putting this condition, this where mi is close to x in this condition, can I make sure that a data point or a centroid will move to a data point only if it is within some scale? So how do I'm trying to convert this algorithm in such a way that I get a scale-based testing algorithm. How do I transform this equation into a scale-based testing algorithm such that a given centroid will move towards a given data point only they are within certain scale? I give you some scale parameter. Okay, so let us give a number like sigma. So that is defined as my scale. Now, just like here, I'm giving the scale. So this value, which is like about 0.2 or something, 0.3, 0.2. I'm saying that is a scale. If I give you that scale, if you run the clustering, you will get 4 clusters. If I give you a bigger scale, like about 0.6 or so, you get 2 clusters. So how can you take this kind of a scale parameter and modify this algorithm in such a way that you get a scale-based clustering? Modify the above equation. Do you have any guesses? Any guess? Okay, so think about this problem.
Maybe like we can like compare that average distance.
What distance? Sorry, what distance again?
That average distance with that scale, right? Average distance.
No. So what I'm trying to say is,
I mean like if we
this is mi, this is data point x. Move mi towards x only if they are within some scale. Okay. Otherwise, don't move. Don't touch it. That means every data point has some kind of a radius of attraction. Right? It will attract mi's only if they are within some radius. Otherwise, it doesn't touch them. So it's a very simple idea, right? How do you incorporate this into the above equation? So basically, what is the previous condition saying? Mi is moved towards x only if it happens to be the closest centroid. So therefore, you don't move very far off centroids towards data point, right? So similarly, another way to constrain it like that is move mi only if it is within some scale. So how do you formally say it? How do you express it mathematically?
So if we give a condition that mi minus x is sigma or is less than sigma, then maybe only centroid mi which is like close to in that particular scale will be the centroid will be allocated.
Yeah, beautiful. So what you are saying is delta mi is equal to eta into x minus mi. Now x is sorry, this is any x and any mi, no more condition, but right, you take any x,
Yes.
take any mi, but make sure that the distance between them is less than or equal to sigma, right? If this is true, right, then apply this update. Is that what you're saying?
Yes, sir.
Yeah, that's very good. So that's what we'll do. Only thing is we'll make a small modification of this. Instead of putting a hard cutoff like this, like a hard boundary, right? It's like only within that sphere, you can move. Instead of doing that, we'll create a kind of a soft boundary, right? By using a Gaussian function, because that has some interesting properties, right? And that's what we'll do in the next class. Okay, so we'll derive an algorithm, which is a nice modification of this to incorporate this intuitive idea. And this is the basic idea. But we realize this idea in a soft fashion and not like using a hard cutoff like this by using a Gaussian function. Because the Gaussian function, what does it look like? It is high within some radius sigma and low beyond that, right? So we'll use a Gaussian function to apply this condition, but in a kind of a soft fashion, right? So you can easily guess what the equation will be if you want to incorporate, implement it like that. So we'll discuss it in the next class. Okay. So any other questions?
Yeah, sir, like I have question on hierarchical clustering. So go to on that slide when we use minimum distance to measure the cluster distance.
Sorry, which slide again? What did you say?
When minimum distance, like when we use minimum distance, like when we use minimum distance to measure the
Oh, that one.
cluster
Okay,
distance.
min 5. Yeah, this one. Yeah, tell me.
Yeah, so like when we are combining single point in like one cluster, like two single point in one cluster, so why we don't combine 0.4 and 0.1 in one cluster?
0.4 and
Yeah.
0.1.
So like first we combine this one.
Yeah.
Yeah.
So next you okay.
Why
You
we
combine
don't?
this two. Yeah. So now let us look at distances. Let us look at say cluster 1 point of view. Its distances to, so there are only 4 entities now. 2 clusters and 2 data points.
Yeah.
Right. So distance between the cluster 1 and cluster 2 is nothing but a distance between the data point 2 and 3. So because this is the closest pair. So therefore, the two clusters are at an advantage. They're actually pretty far, but because we are taking the mean measure, 2 and 3 distance will be equal to the distance of the clusters. So therefore, you merge them. Because distance between
Got it,
cluster
sir.
1 and data, yeah, okay. Okay, guys, thank you.